Section 1.10 is our second to last new model. Our last new model will be next week. Logistic. Logistic functions and models is this section. So to start with, a logistic model has a very funny looking equation, and this is, of all the equations we've done, this is the one you've most likely not seen. Capital L on top, 1 plus capital A e to the negative capital B x. I think it's lowercase a and lowercase b in your book. L is what's called the limiting behavior, and the a value and the b value are not 0. If you let a or b be 0, it turns into other functions. Kind of like if we let a on the last one be 0, we became in line. There's one other word that you might see used for limiting behavior, phrase to describe it. Is it sometimes also called the carrying capacity? There are two basic shapes that this can take on, and they really are just reflections of one another, but I'm doing the same way. I've got them over here. This is one of them, and there is actually a dotted line right here that we are not going above. What is that dotted line right there called? Yeah, horizontal asymptote. And then the other one, I don't know why I started on the left-hand side. I guess I thought I was in the wrong place. Is the same thing but flipped around over here. The top, that dotted line, is at the level L, whatever L is from your numerator. The dotted line is the value L, like the horizontal asymptote y equal L from the equation. On the left-hand one, the b value is actually negative, which means that your exponent is positive. And on the second one, the b value is positive, which means your exponent is negative. Because if you take a look back at the equation, the exponent up here has an extra negative on it. So if b itself is negative, the exponent becomes positive. If the b value is positive, then the exponent stays negative. Okay? But the exponent as a whole itself, if you have a negative exponent, then you have a graph that's actually increasing. And if you have a positive exponent, you actually have a graph that's decreasing as you read the graph from left to right. Okay. A couple other features on the graph is you'll notice, just like the quadratics, these have the possibility, not only have the possibility, but we see it happen, where they change concavity. Right? The pink dots that I've located are places where we are changing concavity. So on the first one, this graph is concave down, and then it's concave up. On the second one, it's concave up, and then it's concave down. And we talked about this, I don't know, the first or second day of class, that the location where it changes concavity has a name, and it's called the inflection point. And we approximated it before, and we're still approximating it now. Okay? Now let me kind of give you an idea of what this is, like in real life, that does stuff like this. All right. There was a cartoon movie, which means that you probably didn't see it unless you have little kids in your house, like I did. It wasn't too long ago, but it was a few years back, where they were taking foxes or wolves, I don't know, from one location to another location to repopulate a forest. You guys know what I'm talking about? You may see this movie. I don't even know what it's called. Okay. What was it called? That's what it was. What was it?
Alpha and Omega.
Alpha and Omega. That was the name of the movie. Okay. This is exactly the idea of what they were trying to do. There weren't any, was it foxes or wolves? Do you remember, Hannah? Wolves is what I was thinking too. There weren't any wolves in this habitat to start with. So it actually would have looked a lot like this equation right here. No wolves. That's why we're along the x-axis. The wolves are introduced, and there's plenty of resources for the wolves to procreate, right? They got lots of food, they got lots of space, they can spread out, no problem. So very, very quickly, the wolf population will increase. But eventually, there's only so many resources in that area. And there will be a leveling off at some point of the wolves, whether it means that wolves just cannot live, they can't survive, there's not enough food, or they're killing each other because there's too many of them, or there's wolves that are simply leaving that area. At some point, there is a leveling off behavior, a limiting value, or a carrying capacity of that habitat. Okay? So that's an environmental example of where logistic functions actually happen. And it's terrible that this is called logistic when we have logarithmic, and we have to be so very careful that we say the right one at the right place. So I'm probably going to screw it up at some point. But it is logistic that we're talking about today. Okay, so let's talk a little bit about the end behavior. We've already done it sort of visually with concavity. If our b value is positive, which means the exponent is negative, then the limiting behavior, the limit as x goes to infinity, is actually equal to L. And if we're talking about the left-hand side as x goes to negative infinity, then the limiting behavior, the limit itself, is 0. And this is where we have the curve. I'll just draw it again over here, like this. This is what we're talking about. So over here on the right, we're at L, and over here on the left, we're at 0. And then on the second set, it's the other image. Your exponent's positive, the graph is decreasing, the b value is negative. If you go to the right, your limit is 0 down here. And if you go towards the left, negative infinity, your limit value is L. Do you guys remember the homework that you just turned in, where there were places where it told you to align the data so that it shifted things kind of differently on the x values? It did that so that it was aligning it back towards that horizontal, or that vertical asymptote at the y-axis, at x equals 0, at the y-axis. You can do that with exponentials as well. You just shift things up and down so that your horizontal asymptote is where it actually falls at. So since we're dealing with horizontal asymptotes here as well, there's a potential for getting to align something differently. So just to be aware of that, that's a possibility with these functions as well. We're going to do an example here. Here's the graph that's not drawn in on your paper, but it is from page 98, number 1. Considering the following graph, part A says to estimate the input value of the inflection point. So it's an estimate, which means that you don't necessarily have to have exactly the same number as your neighbor. But there are things, of course, you can't have that would be wrong, too. So looking at this graph, I know it's kind of small on my screen above. I have the benefit of making mine bigger. Do you see that? Zoomed in. Yeah, right there on the iPad. So if you were looking at this zoomed in, I can't zoom in so you guys can see it zoomed in, though. Sorry about that. It would drive you crazy. You'd be seasick how many times I zoom in and out while I'm working. But looking at that, can you approximate what you think the x value of the location where it changes concavity, the inflection point, would be? So I'm thinking about right here. X value, not y.
Oh.
You were looking at y.
4.
Maybe about 4. 3, 4, something like that maybe. Okay, so write one of those down. So maybe at approximately, I'm going to put 3. Put 4, put something like that. 1 is probably not appropriate, nor is 8, right? It's not at 1 or 8. It's got to be something close to 3 or 4. Part B says to indicate the intervals over which each of the following occurs. Where is it increasing? Where is it decreasing? Where is it concave up? Where is it concave down? Okay, so let's start with them. We'll just go in order. Increasing. Where is this function increasing?
Is it x values?
Yes, x values. We're always doing it with x values. Good clarification. Thank you.
-10 to 4.
Okay, so from -10 to just 4?
Oh, to 10.
What do you see? Till 10?
8.
Does it actually start at -10 and end at +10? Yeah, it's actually negative infinity to infinity. We can't see that whole thing on the graph because, you know, we can't see infinity. But yeah, the whole graph's increasing, right? That's the interval from negative infinity to infinity. The part we see is really from -10 to 10, but it is continuing beyond that. How about decreasing? It's not. Yeah, it's none, not applicable, does not decrease, whatever kind of indication. You still have to write it down so that I know you thought about it and answered that it doesn't have anything, okay? But write down something to indicate that there is no decreasing location. All right, the next thing it says is concave up. Negative infinity to 3. So, or whatever you chose to put on part A, right? This portion of the graph is where it's concave up. So that would be negative infinity to, and I wrote down 3, so I'll write 3 here. And the last piece said to do concave down. And where is it concave down? 3 to infinity. It would be that portion of the curve, roughly, right? 3 to infinity. Any questions on that one? All right. We have an equation on this one. We have 3 parts to it. It says first to decide if the function is increasing or decreasing. Part B says to use the limit notation to express the end behavior of the function. And C says to write the equations of the horizontal asymptotes. So you can use your calculator and graph it if you'd like. That's fine. There's nothing wrong with that. So if you want to put this in your calculator, by all means, go for it. Or you can use some of the facts that we discussed from the very first slides to talk about what's happening based on the exponent. That's really what it takes. So I'm going to do it based on the exponent just to show you that that's possible, and then we can confirm what we wrote down afterwards with our grapher. It's all based on this exponent. Okay? This exponent is negative. What does a negative exponent do to this graph? Does it make it increase or decrease? It makes it increase. That negative exponent tells me that this graph is increasing. So part A is that it's increasing. Now part B says to use limit notation for the asymptotes. End behavior happens on both ends of a graph. So we have our end behavior in our variables t as t goes to infinity, and we have our end behavior as t goes to negative infinity. And this function's name is a of t. So we're going to write a of t beside the limit notation. So we've just said that we believe our graph is increasing, which means it has this basic shape. The 2 end behaviors in no particular order are what numbers? 0 and L. And 0 is just 0, and L is where in the function? On the top, right? It's the numerator, which in this one is 16.5. So we just have to figure out where we're going to write the 16.5 and where we're going to write the 0. So where are we going to write the 16.5? Is it on the first one that I wrote down, t goes to infinity, or on the second one, t goes to negative infinity? The first one. Because this graph's increasing, which means it's leveling off at the high value. So the first one as t goes to infinity is my 16.5, and then the second one would be 0. And then C says to write the equations of the asymptotes. So what are the equations of the asymptotes? Okay, so they're y equals equations, right? So y equals, and I'll have 2 of them, and that doesn't matter the order. but it's y equals the 0 and y equals the 16.5 from the end behavior values we had gotten before. And to confirm this, and to show you that we really can do it without the calculator, I want to show you that the calculator will actually show us that these work too. So go ahead, and I do want to be careful with you to make sure you enter this right in your calculator, because parentheses are really important, they really matter. You keep telling my 18-year-old son how important it matters where locations of things are. He's in pre-calculus right now. I'm not sure he believes me yet. We're just going to keep working on him. So parentheses are going to really matter to your calculator here. So we're going to write in the 16.5. I don't need any parentheses around that. It's a one single value in the numerator. It's fine. However, the denominator has a lot going on, including addition and subtraction. If there's any addition, subtraction, multiplication, division in the denominator, you need parentheses around the whole denominator. Now, some of your calculators automatically put a denominator notation in there. Yay for you, because that helps organize your information. So in your denominator, you need the 1 plus 1.86. Your e is over here underneath the natural log button. See it up here, e to the x? So you have to hit your second button and the natural log button to get the e, and it's an e with a caret that shows up. Now the parenthesis after this is going to indicate that everything from the exponent needs to be written inside of here. So my exponent includes a negative 0.43 and an x, and then I close the parenthesis for my exponent, and then I'm going to also close the parenthesis for my entire denominator because my calculator is set up that way. I don't have any real good idea on my window except to say that I believe that my window doesn't need to be negative. Okay? I meant my y value, sorry. My y value doesn't need to be negative. And it shouldn't need to go above 16.5, right? So I'm going to make my y max 16.5. And I have no idea what I want my x min and my x max to be, so let's just leave those as negative 10 to 10 and see what happens. And we'll graph it. That's not too bad. If we want to see a little further out on the x-axis, we could. I can make my window, say, go out to 20. It is increasing, right? Indeed. The limit on the left-hand side is 0, and the limit on the right-hand side is the 16.5 that I put in as my y max. And the horizontal asymptotes are, in fact, y, 0 and y equals 16.5. So this is like the back of the book at your fingertips. And it's not even an even problem, or an odd problem, right? Yeah, right? Like you can check. Cool stuff right there. All right, any questions on that one?
How did you get to 0 again?
How'd I get what?
The 0? Or the it's just because it's going negative? Or
Because it's the y value.
oh.
It's leveling off at the x-axis, which is the y value of 0. That's how. Yeah. Any other questions? Okay, let's do an example with data values. All right, I'm going to read it without showing it to you because you guys have it there with you too. The following table gives you the total number of states associated with the National PTA organization from 1895 to 1927. Actually, I do want to show you something because there is a detail with this one that's interesting. Part A says to examine a scatter plot, estimate the limiting value, estimate when the inflection point occurs, and then eventually we're going to find an equation for this. The first thing we have to do is we have to enter this data into our calculator, and it's a little bit weird. What about this makes this weird? It's not like the ones we've done before with years as the input. Yeah, there's 1800s and there's 1900s. Do you guys see that? So there's several things we could do. We could say align this to the year 1890. That'd be okay. But it feels kind of weird to do that. My suggestion is let's line this to the year 1900, and let's have a couple of inputs that are negative, and that's okay. I think, Hannah, you were the one that asked me about it last time, is can you have negative inputs? And I said, yeah, we're going to have one pretty soon. This is the one I was talking about. So my suggestion is that we let this 1895 one be -5, and the 1899 would be -1, And the 1903 then starts me out with 3. Then I have 3, 7, 11, and so forth. Yes?
We can align the data any way we want. but
You
I just wanted
can,
to say that-
as long as you say it. So if you don't like to have the negatives in there, that's okay. Just make sure that when you're writing out your X years since, it matches what you have.
Okay.
So, I mean, don't get super creative because then you're going to make grading a nightmare for everybody, okay? But yeah, there are some reasonable things that if you chose to align it differently, it would still be fine.
Okay.
In fact, the grading that the grader's doing for me right now, some of you aligned yours differently than I did in a particular problem, and we had to calculate that, so that it did actually happen recently already. All right, so let's enter this. I'm going to use my negatives since I suggested that, and we're going to put this into the calculator. So mine are going to include -5, -1, and then the years after 1990, 3, 7, and so forth. Do you guys know what this, I mean, I always think more about looking at context of things now that I have children in my home who wouldn't know what our acronyms for things mean. Do you know what PTA is? Parent-Teacher Association. So it's the parent associations in public schools is what it really is. Just checking. All right, so we have our data set. We're going to do Zoom 9. And we have what very much looks like a logistic equation, right? Now, I haven't shown you can do this, but you know you can trace, but did you know you can trace and jump along your dots? You can. So let's say you're already right here and you're like, okay, I want to trace and see the inflection point looks like it's around that one. Or maybe you think it's the next one. It's got to be one of these three. You don't have any other choices, okay? I think it's probably most likely the 11. That's what it looks like on mine, is that that's where the concavity changes. So we would write down that we have an inflection point occurring at about 11. And then what is the limiting value in terms of the context of this problem? Can you figure out what the limiting value would be from context only? $50. Why? Because there are 50 states. That's exactly right. So if we're looking at the limiting value, we have several questions. It said examine a scatter plot. We did that. Estimate the limiting value. So our limiting value we believe to be approximately 50. And then it says to estimate the inflection point. So the inflection point is somewhere around 11. What was it at 11? 23. So this is what we estimate. So what does that mean? What is 1123 in the context of what we're doing? 1911. So it says estimate when. This would be the year 1911. If you aligned it differently, yours might actually have a different X value, but it would still be the year 1911. Okay. Estimate when the inflection point occurs. Part B asks us to find a logistic model. We already have our data in here. So let's go through the steps to find our logistic model. I had mentioned earlier that it really matters on years that you don't put too big of values in. It's this function that it matters the most for. Your calculator has to go through a lot of numerical integration, a lot of steps to get this particular function because it is a complicated function. And when the inputs are too big, it freaks out. And in fact, it'll usually say something like overflow, data overflow. That means you've got too big of values somewhere, okay? All right, so let's go ahead and go through this. We will hit Stat, Calc, and if I arrow down far enough, it actually says Logistic. You don't have to remember anything, it just says it on this one, Logistic. And tell it to put it into Y1. You can even say see how long it takes? Compared to the other ones, this happens very slowly. And you can see that it has a c on top, 1 plus ae to the negative bx on bottom, and those are all my values. Now, if you aligned it differently, your numerator, your c value on top will still be the same. It'll still say, oh wait, what happened here? Oh yeah, 49. I was looking at the wrong number. It'll still say 49.26397022. That'll be the same. But the other parts will be different.
Another island, it was 52, beyond 49. That's 1895.
Yeah. Check your subtractions again for 1895.
That was just the difference.
Oh,
Or
there's no difference of 4 originally.
yeah.
Okay, yeah, there's something wrong with it because if I add your 1895 back to it, the first few are right, but then we're going to get another call.
Alright.
So check that out, that's what's going on. Did anybody else have anything that didn't show up like this? No? Okay. All right, we have our equation, let's jot this down. This is the number of states, so I'm going to call it S, very clearly not a 5, because S's and 5's can look a lot alike, but I'm going to call mine capital S. My numerator is 49.264 over 1 plus my A value is 9.392 E. Now remember, the negative is in the equation, so there's still a negative even though the B value on your calculator shows a positive. So it's negative 0.184 x for my exponent. Now what? States. And the way I did it, it will say where x is what? Yeah, x is the years after 1900. Whoops, running out of space there. And then my interval would be -5 to 27. And then it asks, according to the model, how many states were associated with the National PTA in 1965? So with this alignment, what would I be plugging in to find that out? 65 in for x. If you did it as years since 1895, like Lucas was suggesting, you would have put in 40, right, Lucas? Right? You would put in 70.
Yeah.
Did I say 40? I don't know. 70 is what I meant to say. 70 on that. Yeah. Okay, so S of 65. So I'm going to go into my table. I'm going to plug in 65. When I do, my calculator says 49.261. How many states would that be? 49, because we don't have 0.261 of a state. Not exactly sure how we count some of our territories, but they don't count because they're not states. They're not partial counting, okay? So this would be 49 states. Any questions on that one?
Like, why wouldn't you round up?
Yeah, it's kind of tricky, because there's not a real good reason. Like on the last one, it made sense for us to do the blenders, remember? Where we rounded up instead of rounded down, even whether we were ignoring the decimal points or not. And there's some cases where it simply just, it almost doesn't matter. Our model's predicting this, and we don't have a clear indication in terms of context whether to round up or down, so we just use our normal rounding rules when that happens.
Okay.
Yeah.
So, I mean, are you gonna count off if we did?
If you wrote down 50 states here, it's just, I mean, no, it's okay. But you do need to round to a whole number of states. That I will count off for if you tell me 49.3 states or something, that would be a problem.